Good afternoon, everyone. My name is Afifa Hanum Amahodu, and my team leader here is Ang Mo An. We are from Korea Institute of Ocean Science and Technology, or KIOST. Today, I will present our project titled LSTM versus Transformer Encoder, a controlled comparison for news topic classification. Both LSTM and Transformer are widely used for natural language processing. However, most previous studies compare pre-trained models, such as BERT, making it difficult to isolate the contribution of the encoder architecture itself. In this work, we compare bi-LSTM and transformer encoder trained entirely from scratch, while keeping the dataset, pre-processing pipeline, vocabulary, and training settings identical. Therefore, our main research question is, when both models are trained from scratch under identical conditions, does the encoder architecture alone lead to different classification performance? To answer this question, we evaluated both models on the AGNews text classification benchmark. This slide summarizes our dataset and experimental pipeline. We use the AGNews dataset, which contains 4 balanced categories: work, sports, business, and science and technology. Following the recommended protocol, we split the original training set into 108,000 training samples and 12,000 validation samples, while keeping the official 7,600 test samples only for the final evaluation. To ensure a fair comparison, both models used exactly the same processing pipeline. For example, consider the sentence, Apple unveils a new AI chip for future MacBooks. First, the sentence is tokenized into individual words. Each token is then mapped to its corresponding vocabulary index, pad or truncated to a maximum length of 128 tokens, and finally converted into a 128-dimensional embedding vector. The processed input is then fed into either the bi-LSTM or the transformer encoder. Therefore, the only difference between the two models is the encoder architecture, while the dataset, preprocessing, optimizer, training settings, and evaluation metrics remain identical. After applying the same preprocessing pipeline, we compare two encoder architectures under identical training conditions. Both models start with the same 128-dimensional embedding layer and end with the same linear classifier. The key difference lies in how they encode the input sequence. The bi-LSTM processes the sentence sequentially, updating its hidden states one token at a time. The final representation is obtained by concatenating the forward and backward hidden states before classification. In contrast, the transformer encoder first adds positional encoding to preserve word order. It then applies multi-head self-attention, allowing every word to interact with every other word simultaneously. The final sentence representation is obtained using mean pooling before classification. To ensure a fair comparison, both models use two encoder layers, the same embedding dimension, the same dropout rate, and a comparable number of trainable parameters. Therefore, the primary factor being evaluated is the encoder architecture itself. Next, let's compare the overall performance of the two models. Looking at the performance table on the left, both models achieved almost identical results on the AGNews test set. The bi-LSTM obtained a macro F1 of 92.25%, while the transformer encoder achieved 92.29%, resulting in a difference of only 0.04 percentage points. The training curves further support this observation. Both models converged smoothly within 10 epochs, and the validation macro F1 curves almost overlapped during the later epochs. indicating very similar learning behavior and stable convergence. Finally, the confusion matrices show that both models classify the sports and science and technology categories very well. However, the largest source of error for both architectures is the confusion between the world and business classes, likely because many news articles contain overlapping political and economic content. Overall, these results suggest that on the AG News dataset, the encoder architecture alone does not create a meaningful performance difference. Since the main comparison showed almost identical performance, we conducted an ablation study to see whether the two models respond differently to regularization. Here, we compared the default setting with dropout 0.3 against the model trained with no dropout. From Table 5, removing dropout increases the performance of both models. However, the decrease is larger for the transformer encoder. The LSTM drops from 0.9225 to 0.9111, while the transformer drops from 0.9229 to 0.9048. The validation F1 curve spots the same finding. Without dropout, the transformer curve stays lower than its baseline, showing stronger degradation compared to the LSTM. This suggests that the transformer encoder is more sensitive to dropout removal, probably because self-attention has a higher capacity to memorize token patterns. Therefore, the clearest architectural difference in this study is not final accuracy but regularization sensitivity. To conclude, we performed a controlled comparison between a bi-LSTM and a transformer encoder, both trained entirely from scratch under identical experimental conditions. Our results show that both models achieved almost identical performance with approximately 92.3% macro F1, indicating that the encoder architecture alone does not create a meaningful performance difference on the AG News dataset. We also conducted 3 ablation studies. The dataset size and encoder depth experiments showed very similar behavior between the two architectures. In contrast, the dropout ablation revealed the clearest difference. The transformer experienced a large performance drop when dropout was removed, indicating a stronger dependence on regularization. Overall, for short text news classification, both architectures are effective. However, when training transformers from scratch, proper regularization is more important than the architectural choice itself. Thank you very much for your attention.